their way up to the front here. First off, welcome to East question mark Bay Rust. We'll see about that, how long that East lasts. But for right now, we're going to keep the name. This is our second meeting together. So it's already recognize some faces. So good to see you all again. And hi, yes. And I wanted to start by handing it over to, say some thanks to our host today, Convex. Yes, let's do applause. Yeah, yep, thank you. Go Convex. Thank you for offering this lovely space and this lovely event and everything like that. And Jamie, you.
Sure. Yeah, hi. Welcome to Convex. Does anyone here know what Convex is? Out of curiosity? Okay, it's a few hands. Convex is a new kind of cloud abstraction for doing backend stuff. It's fun, it's cool, but crucially for this group, we write a lot of Rust at Convex, and so part of my job right now is to shamelessly try to tell you all, come work here, please. So we use a lot of Rust. We love Rust. If you like interesting systems problems in Rust, this is a great problem and a great crew to work on them with. So a lot of the sort of bona fide stuff of this group is like a lot of us worked together at Dropbox for a number of years, introduced Rust at Dropbox in like 2014, which was pre 1.0, super scary, and built out a lot of the storage system at Dropbox with Rust, and then moved into building a lot of the sync engine in Rust. And so there's people here that worked on all those things. So anyway, yeah, this is Convex. Thank you all for coming. We're very happy to host events like this. We love Rust engineers. And, we might as well go to convex.dev/jobs and check it out. Maybe, who knows, maybe you'll like it. So thank you.
Thank you so much, Jamie. Yeah, do some applause. All right, and with that, I would also recommend joining our Discord server. We're kind of getting it going, starting the engine, but definitely wanted to make it a space where people can learn things from each other, post jobs, find people in the area who might be looking for things, especially right now. So if you're interested, we have this, and I'll put it up again later. Agenda for tonight. Well, we've already got the pizza. I can see a lot of people are enjoying it. We're going to be doing 4 talks. Going to be like 10-15 minutes each. And then we're going to have a little Q&A section at the end for everybody to chat and kind of see how things are going. And then we're going to just hang out and we're going to see how the night goes from there. So yeah, without further ado, I'd like to introduce our let's see here. I'd like to introduce our first speaker, Nipunn Koorapati, software engineer here at Convex. If you'd like to come up and thank you.
Yeah, and I got this guy. Perfect. All right, cool. Hey everyone, I'm Nipunn. I'm an engineer here at Convex. I've been at Convex for like 4 years, for quite a while. I am filling in for Emma, who was originally going to give this talk. They're the tech lead on the infrastructure team here. They kind of had a last second family emergency yesterday, so they had to fly out of town. They were really looking forward to giving their talk, so they'll probably give it at a future meetup, and so looking forward to that. I'm going to do they had to fly for a family emergency in San Diego. I'm going to do a little funny thing. If you want to play along, please do, but if you could make a little heart, we could send some love to Emma. They're in San Diego. I think it's that way. I think that way is southeast, so I'm just going to do that. All right. I will get started. I'm giving a talk on abstractions. I sort of threw it together today. It's thoughts I've been having for a long time, but I threw the talk together today, so cut me a little slack. Cool. So I'm going to start with what is an abstraction? I feel like we know this word, but we're going to really get into some examples. An abstraction, I think, is something that hides something that contains wisdom. I look at this example. This is a photo from our office over on the other side of our coffee machine. And if you've ever looked inside of how one of these work, they're kind of ridiculous. They have a lot of stuff going on. one of the ways I like to think about the way, this is an abstraction. This is clearly an abstraction. There's like a few knobs on the front and there's like a lot of crazy stuff going on inside. I think good abstractions come from this place of like ruthlessly, repeatedly asking yourself, like, how can I make the interface 10% simpler? Like, can I make the outside 10% simpler, even if it makes the inside 20% more complicated? And you just make that, you try to do that as many times as you can to make the outside as simple as possible. This is a good example of an abstraction. You push the lever and the bad stuff goes away. As a recent homeowner, I started to learn about how the stuff inside of this works, and I like honestly didn't know. And there's like different ways. It's a really good abstraction. You push the button, the bad stuff goes away. Most people don't have to think about it. Abstractions let you not care about what's under the hood, and in this like literal sense, like if you have a car, there's lots of stuff going on. Well, in an internal combustion engine, this is like lots of stuff going on in this type of car. But it makes it so you don't need to know about it. And like most people don't know what goes on under there. And also we like in the last couple decades have made other types of cars that have totally different things under the hood, like electric cars and hydrogen cars and things like that. So it really does allow like you to separate the concept of like driving the car from understanding how it works. And again, this is like, again, doing this like ruthless, make the inside 20% more complicated to make the outside 10% less. It's like when you're using an abstraction, like I feel like it's a meme, so don't read too hard into it, but I feel like the general idea is that like if you don't know how it works, the abstraction's great, and if you really know how it works, you also really appreciate the abstraction. Sometimes in the middle, you think you know more than you do, and you like wish you could break the abstraction so you could do something funny with it. And I think with good abstractions, usually at some point you get wise enough that you're like, I'm happy with the simple thing. My little joke here is like, I feel like the software engineering world is going this way. Like, especially with agents coming in, I feel like the left side and the right side are like two archetypes for types of software engineer in this world. Like, this is just happening. So this is a quote from Edgar Dijkstra from 1972, like a famous like software engineer, and it's talking about the software crisis, which is this thing where there's so much software in the world that like people can't figure out what's going on with it. And he like really pointed this out. And this is like the era where there's like programming languages have go-tos everywhere. Like there's not really concepts of functions, and like really called this out. It's like there's an explosion of like what computers are capable of doing and what software is capable of doing, and it's hard to keep up with. It should sound familiar. And then maybe like a decade later, this is like a quote from Barbara Liskov, who's a famous computer scientist. Also happens to be our CTO's PhD advisor. It's kind of cool. The main idea is to separate what the abstraction is from how it's implemented. It's kind of common sense now, but I think in this era, it was kind of a big deal. It was like a thing that you have to keep repeating and like kind of bring into the, like, you have to make functions. Shouldn't care how the function is implemented. So I think this is like, I mean, I consider this like the gold standard software stack. Like this is one we've had for a few decades, and like you have a client, you have a server, you have a database. Like if you're building something, you have like the LAMP stack is like from the 2000s. We set things up in this way. And it generally works pretty good. Your client doesn't have to think about how the server works. The server doesn't have to think about the database works. You generally have a pretty good stack. Most mature code bases end up with more abstractions on top of this, because even with this, there's like a number of guns. I just named a few, but like, what happens if your server crashes mid-request? Does the database handle it? Like, if you have a transaction open, the database is supposed to roll it back. But if your server code has multiple transactions and it calls out to a third-party service halfway and then you crash, like, where does it end up? Like, how do you ensure that your client gets updated data if a different client mutates the data on the server? How do you keep these in sync? And then this last one, it's like databases have sort of abstractions that they give you, and even like most production applications set up like databases in, I don't know, different modes that are not the full serializable mode, and they end up with different abstractions than the ones that seem obvious. So there are footguns here, but also like this is stuff that if you've worked with systems like this, you're kind of familiar with, and like honestly, it's like why we get paid the big bucks. Like we have to like know about these footguns and work around them, and then use the abstractions to like help us out here. One of the things Convex does that I think really helps in this era is that we kind of rethought the right half of this diagram, like the server and the database are pulled into one abstraction, and the concept of a transaction exists like within a single request that you push code into. There's a lot more details about this. I sort of copy pasted a diagram that we had internally from a while ago. A lot of the details of this is like actually what Emma's talk was really going to be about, so stay tuned because that will come. But I really wanted to zoom out and think about like how this fits into the abstraction mindset. Because one thing that we've noticed like is that I could really bifurcate our customers into like two kinds of groups. Like there are kinds of people that love Convex are often like you've got your I don't know, like young Y Combinator founder who's like never made a thing before, and they're like really they're like uh, they have a lot of tenacity and they like really attack the problem. And especially with agents, can spew out like a lot of code and like really like try things in a lot of different ways. People like this love Convex because their agents are like way more successful because it has more guardrails and it like kind of prevents you from these footguns that require wisdom that you don't have yet. And then also on the other end, like very experienced people tend to like stuff like Convex a lot too because they understand what the footguns are, and they, even though they know how to avoid them, they don't want to spend that effort like you, you're not solving the problem at hand when you're like thinking about, I don't know what the data consistency model is. Or if I were to say it like kind of jokingly, it's like the left person doesn't care about like a 1 second transaction limit, and the right person doesn't want more than a 1 second transaction limit because they know where that road leads, and the person in the middle kind of wishes they did. But, yeah. So, okay, so I'm going to move on to talking about abstractions in code. So I have a little code snippet here. This is actually something I was working on today. Like I grabbed a piece of code, I simplified it, but I grabbed out of it something I was like looking at today. We have like a concept of a deployment, and the deployment can be in a running or a like deactivated or like deleted state. And when a deployment is running, it is assigned a partition, and when it's not running, it's not running on a partition. And so in our database, there's sort of two columns. There's the state column and the partition. When you pull it into the code, like the naive way to describe this would be to have a struct with two items in it, and one of them is optional. But there's sort of like the two states are connected. Like a partition only makes sense if the state is in one of the two states. And in Rust, there's this a really natural way to describe this using like an associated in enum. And so this technique, like Rust really gives a lot of good ways to handle things like this. And in our code base, we do stuff like we use a struct like the one on the left when we're interacting with the database, and then we like hide that within the module and use like a struct that's on the right when we're interacting with the rest of the code base. Like I like really love Rust for things like this because like structs are abstractions, objects are abstractions, functions are abstractions, and like good abstractions you have to like really think about and design. And I think those good abstractions are like the simple APIs that hide the tricky thing behind it. It's like the one lever that makes the bad stuff go away. Like it's the same idea. So I think I think Rust and languages like it that give you ways to provide good abstractions that put guardrails on what your code can do become more important in an era like now where the volume of code being produced is just going up really high. So going back to this software crisis quote, there's gonna be a lot of quotes today. So software crisis quote, like 1972, the volume of code is going up like really high. This is another quote from me. I made this up today. LLM agents underwrite code that look and feel like they have the abstractions that we're used to, of code that we're used to. But when that abstraction is leaky, the LLM agents take no responsibility, and it's us that have to pay for it. If anyone's familiar with the subprime mortgage crisis from 2008. How do we solve the subprime code crisis? I'm of course here talking about LLM generated like large volumes of code. And I think the answer here is we have to up our game on abstractions. Like when Dijkstra was talking about the code crisis, it was like we have to write functions. We can't just like put everything in one function. We have to make functions. I think we have to up our game on this, like as an industry. So like one of the things I've noticed like is that this kind of change, this is a simple one, but like using it as an example, this kind of change, you end up in the world on the left kind of by accident. Like usually if you could design things from scratch, you'll end up in the world on the right. But often you're like adding things on and you add the concept of the partition later and then things get kind of glued into your code base and you end up in a world where you have invalid states that are representable in your system. And the process of converting from the left state to the right state is tedious and maybe annoying. You might consider it yak shaving, and there's like always more of that to do. And it can be like a little hard to either like motivate yourself to do it or convince someone else that it's worth the time. And like, it's kind of reasonable logic. But one of the nice things about 2026 is actually something I've been thinking about for the last month. I went to the last the East Bay Rust meetup, and Michaela had a very good quote about this. 2026 is the year of the yak shave. I think she's right. Like the point is that like it's easier than ever to do a refactor like the one we were describing on the previous one. Like you can just send a thing off to go do it. Or if you're not even sure if it's a good idea or not, you can still send an agent off to go do it, and then you can go check in later, maybe sleep on it, see if it's a good idea. And so I think while at the same time we have the volume of code going up, our ability to enforce better abstractions is also going up. We just have to be willing to do it in a way that maybe didn't feel worth it before. So we have to just adjust for it. Yeah, so or in our prolific code era, the abstractions give better guardrails, and I think we can use that to make higher quality code. Now, of course, I think there's going to be there's going to be more code bases than ever that just have like crazy, I'll call it low quality code, but like just stuff that's like no one's looked at and is like a little bit crazy. But I also think our ability to make high quality code should improve, but we got to like do engineering. So that's just things I've been thinking about in the last months here. Cool. I gotta put this slide here. Emma would be mad at me if I didn't fill this one in. This is a topic I've been thinking about a lot. Like we were just talking about it today at our team meeting. Like people matter. Like we're building this so that people can make applications that are good for the people using them. Like we built Convex because we think better abstractions help like a developer. And now like a lot of the developers are using a lot of agents and LLMs, and I'm like kind of sick of seeing billboards that are saying things like, I don't know, like replace your sales team with a sales team of agents that don't have to take PTO or need healthcare. And I'm like, just like I think somewhat at the core, like kind of like believe that like we're making software so that like the software is for people, and like the software that helps you make software is for people. So I like believe that at the core. So a bunch of other things here. Good taste. We believe in taste, and like we believe that we have wisdom that we can encode into the abstraction so that people using it don't have to have that wisdom. So we learn, we figure this out. Anyway, thank you.
Thank you so much. yeah, for that lovely talk and also for the surprise quoting. It was very good. Lovely. I believe, yeah, we're doing Q&A at the end, right? So I guess we're moving on. All right. Well, thank you so much, and thank you for Convex and everybody there. I believe up next is John Notgull, or John Gull? Notgull, okay, make sure. John Notgull talking about Sans IO abstractions and yeah, all that stuff. welcome up.
Hi, everybody. Hello, everyone. Today I'm here to talk about Sans IO and code deduplication in a way that I think will matter a lot for the Rust community. Before I start with that, just quick question for everyone in this room. We got a room full of Rust developers, so this is the perfect place to ask this question. Who here has looked in their dependency tree and saw two crates that, as far as you could tell, did the same thing? See, show of hands. All right. Well, wow, we got a lot of hands here. So I think we all agree this is a pretty big problem that's happening. So I'd like to talk about this problem, how it happens, how we can fix it, in a very special time that I was involved in fixing it. But before I start, obviously you want to know who I am. First, here's some quick disclaimers. Just read through them, absorb them with your eyeballs. Main thing, just all opinions expressed here do not reflect my employers, past, present, or future. We're good? We're all adults in the room? Great. Okay, so first you're probably wondering who I am. I'm notgull. I have a blog that you may or may not have seen. My posts tend to fly across the cybersphere like seagulls over the bay. I've contributed quite frequently to the Rust open source community, which you may have interacted with some of my crates. Most notably, I've contributed a lot to Small, and I've contributed a lot to the Winit windowing framework, specifically the Windows and X11 backends. Now, let's talk about the actual problem. There's just a lot of crates that seem to do the same thing. For example, here's me with a fresh install of a package. I decided to grab Xylem because that's a pretty big crate. And as you can see, we have 257 unique dependencies. I think we can all agree that this is a mass number of dependencies. I'm not saying that 0 dependencies is the ideal goal. In fact, I would prefer to say the opposite. I think 0 dependencies is as bad as 1,000,000 dependencies. 0 dependencies, you're going to have to rewrite a lot of basic stuff, and that's not good for anyone. But hundreds of dependencies is also bad because that's code you can't audit. That's code you have to audit in order to make sure your application works. Dependencies weigh your code down. So in order to drop it, something a lot of people will see is you go through these and you see crates that, according to you, might seem to do the same thing. The biggest example I've seen of this is ByteMuck and Zero Copy. Both these are crates that treat plain old data as bytes and treat bytes as plain old data. This comes up a lot in GPU rendering because you have triangles and you need to pass those triangles as bytes to your GPU. Another one that I've contributed to, Small and Toke.io do roughly the same thing, albeit in very, very different ways. And I'm sure you can think of other examples too. For example, TinySkia and Rakote, 2D rendering libraries that do roughly the same thing, CPU rendered 2D graphics. Those are the obvious ones. And this causes some immediate issues. I mean, materially, it's just the more code you have, the longer its code takes to compile. But there's a more sinister issue at play here. So I would like you to imagine for a second that the Rust open source community is a massive corporation. Clearly, it's not. And this metaphor doesn't work for a lot of use cases, but bear with me here, imagine it is. If you have two people working on similar products doing roughly the same thing at a large corporation, that's wasted work. You've spent hundreds of thousands of dollars on a programming resource. And that programming resource is spending 40 hours a week at least on some amount of effort maintaining their project. And one of those employees may as well pack it up and go home because they're wasting their effort when one person's doing everything otherwise. So if you have two projects like this, you can see that the effort will be split between these two projects. So the solution to this is to merge them together, create one combined project. That way you get double the effort into the single project. So for example, if two people were previously each maintaining their own project, maybe now one person can handle new PRs, handle new features, just put more effort, or their effort is freed up to work on something that might be more useful. Of course, this is a very idealistic thing. There's a lot of ways that this can go down, right? Combining projects like this. The first and frankly most common way is that it's just not possible. Both the crates have different enough ethos that you can't really do anything with it. You can't take it. You can't you can't make one cooperate with the other in any way. This happens. They just don't gel together. One crate likes dependencies. One crate doesn't like dependencies. One crate uses edge triggered events. One crate uses one-shot triggered events. It happens, unfortunately. Something else that happens is subsuming. One crate can be reimplemented entirely in terms of another crate. I'm sure some of you will remember async STD. This is one of the first async frameworks that hit the Rust open source market. The async STD was re-implemented recently entirely in terms of small. So if you're using async STD today, it's just a thin wrapper, a new API wrapper around the small runtime. Now, my favorite thing is factoring. You have two crates that have different enough design philosophies that you can't share all the code, but just different enough that there's some code that you can extract out, some kernel in there that you can take out and share between them. I really enjoy when this happens. When you have two crates written by two different people, both expressing a different design philosophy, cooperating, working together, and factoring out some code. And this is what I would like to talk about today, but first I would like to talk about what made that possible, Sans.io. Check out this diagram I created in Krita. We use open source software here. Now, what is Sans.io? I'm sure we've used IO traits in Rust before, right? Read, write, or if you're a fan of async read, async write. We've all used these various traits, but these traits are abstractions, like the previous speaker said, abstractions to something else. And of course, these abstractions necessarily need to deal with tricky use cases that happen in the real world, right? Like the socket suddenly getting closed, or the file is on NTP drive, or even worse, someone yanked out the USB stick at the very last second. You have to deal with all these weird, wacky use cases, but what if you didn't have to deal with that, right? What if instead dealing with, IO, dealing with these traits, you just dealt with bytes. You design your code in such a way that it reads, you give it a byte buffer that represents whatever the user is giving you, and it gives back the bytes to send back over your socket. This is what Sans.io aims to do. It aims to get rid of all that messy IO layer and replace it with a nice, fresh, clean byte abstraction, which is substantially easier to test, usually substantially smaller, and substantially more interesting. I'd also like to talk about X11. We have a pretty good sampling of programmers here. Who here uses desktop Linux? Okay, keep your hand up if you're currently using X11. Now raise your hand back up if you're using Wayland. I think it's fair to say Wayland's won. Wayland has very much triumphed over X11 in most cases, but unfortunately we still need to keep around the X11. A fair number of applications are stuck on it for various reasons. FreeCAD specifically has been stuck on X11 since Wayland's founding due to Wayland not having some features that FreeCAD needs. So we're going to deal with X11, and X11 is hard. I mean, anything that's been around since 1984 is going to be hard. I think we can all agree on that. But X11 is specifically its own layer of difficulty. I'm sure some of you in the process of using Unix have deal with Unix signal handlers, common state shared by the entire process for a resource that a lot of parts of code are going to need. If you've ever had to handle the control state signal, you know what I'm talking about. I want you to imagine that level of global state for error handlers, except there's no way to tell if you're replacing a previous error handler or not. X11 is hard, not to mention there have been 31 extensions to X11 in the past 50 years since it was introduced. A lot of it is necessary, and a lot of it is very, very, I believe the words the kid use is jank. Look at this. I decided here's an implementation of the X11 profile I'm going to talk about later. Spoiler alert. You can see in total, it takes us 128,000 lines of Rust to fully implement the protocol. That's more lines of Rust than there is in WinIt to implement X11. Granted, a lot of this is automatically generated code, but a lot of this is also, protocol handlers, dealing with edge cases, so on and so forth. Point being, X11 is complicated. So I created something called breadx. I believe that's on the previous slide. Yeah, I wrote breadx. I took my favorite thing and added x to the end. Now, breadx was my attempt at creating a better interface over X11. The goal being, first, it would have no mutexes, which is the fastest way of doing things. Second, it would be implemented in pure Rust, which I managed to accomplish. You could now communicate with the server in pure Rust. And third, it would use a minimum of dependencies and support async programming, which I believe I accomplished. I was able to use it in some not production applications, but I was able to use it to throw windows up on the screen. And the competitor of that was X11RB. I say competitor, I mean that in the friendliest possible term, not like competitor at a company, competitor in team sports. Written by Sycon, otherwise known as Uli Schlatter. It was a very basic implementation. It was generally meant to be an interface over XCB, which is the main binding to X11, but with some additional features to allow for, if you wanted to use pure Rust, you could. If you wanted to use mutexes, you could. A very different design ethos. Now, of course, seeing this, we both had to create all this code. I had to write my own X11 implementation. He had to write his own X11 implementation. That's a lot of code, a lot of work that both of us are doing for no reason. We're writing all this X11 protocol code. I'm rewriting it for no reason. It's a waste. So, upon realizing this, circa 2022, I reached out to Uli, and I said, "Hey, I have an X11 implementation. You have an X11 implementation. Let's split some of it out. There's a lot of code that we could share here that both of us could very easily rely on to save both of us a substantial amount of time." And after working out the details, after hashing out the details, and he agreed. So we got to work, and we split out basically all of the X11 actual protocol implementation into a completely separate crate, X11RB. Of course, this used the sans IO principle, right? No IO, it's just manipulating bytes. This is very important here, right? Because the way we did IO, as I mentioned, was very, very different. One person was doing it with mutexes and only doing it synchronously. I was doing it with no mutexes asynchronously. So we need to have very, very different strategies. So I decided to split out all that code, plus a lot of the protocol code, a lot of the code that says if you receive this byte, do this. and we split it out into its entire protocol. When I say protocol, I do mean protocol too, because X11 is a network protocol. And the end result was this beautiful thing, this combination of both of our efforts. 0 unsafe code. It can be used in BreadX. It could also be used in X11RB. Now, I believe this is a shining example of Sans.io, just because we can now split a ton of code. We've taken all the code that we were working on, all this duplicated effort, all this wasted time, and put into one place that both of us can work on, both of us can easily maintain. Of course, I like to look for a lesson in everything. So here is my lesson from this. Collaborate. I know it might seem a little nonsensical. This is open source after all, but I do feel like there's a lot of lot more collaboration that could be happening. If you're creating a crate, don't try to deduplicate it. Don't say, hey, I'm creating a crate, but this crate basically does the same thing. No, try to find common ground. Try to find common ground. Try to find the best way to express your API in a way that works for you, or they can express their API that works for them and share some code. That's what this is all about, after all. Okay, I'm not sure how much time we have left for questions.
Yeah, we can take some questions. I actually also had one.
Hit me.
First off, thanks for maintaining small. We use that. That's Ed. Very lovely.
No problem.
And I know in async Rust, there's a big problem where if Tokyo's in your dependency tree, it's like you gotta use it, right? Because of the way async Rust is structured. Do you think Rust makes this sort of Sans.io patterns easier or harder, or how do you think that works?
I do think it makes it easier, right? I mean, obviously, Sans.io was born with Python, being able to pass around Python types, being able to easily pass around buffers. It was born in Python, but I think it does work well in Rust, if only because Rust is very, very good at composition, and Sans.io makes composition a very big deal. It's very easy to have a trait that can be expressed in one way or another. It's very easy to have like, for example, if you really want to have a trait that implements the core logic of your application, then write a Sans.io a crate that takes that and uses that to do the I/O. I think it's definitely easy. There's definitely languages that do it better. I do feel like Sans.io is best suited for things like Python. I do feel like Rust does it fairly well.
Okay, fantastic. Thank you. Any other questions? Okay.
All right, thanks for the talk. So one of the examples that you had was saying if you've got two crates that, there's a lot of echo here. If you've got two crates that have common logic that could be factored out, right? You started with two crates, and now you factored out that logic into like a common dependency crate. Now you've got three crates, so you actually increased your dependency count, even though you decreased the amount of code in your dependency tree total. So how do you consider and weigh the trade-offs? This is definitely an issue I've come up over and over again as a maintainer of a large library.
Right. I definitely see the issue here. However, if it were up to me, I'd rather drink 5 cups that each have 1 milligram of poison than 2 cups which have 5 milligrams of poison. Very much practically speaking, more crates is not necessarily a bad thing. I brought this up at the start. If you have 0 dependencies, well, first off, it's actually bad for the build. I'm sure some of you know that Rust compiles crates in parallel. Each crate in Rust is considered a code gen unit, and it usually goes 1 code gen unit per thread. Granted, modern Rust compile is able to break it up a bit more than that, but that's still a decent rule of thumb. And so theoretically, this would build faster. But also, I feel like dependency count can be a bit misleading because, like I said, if you split it out into a few crates, right? Well, previously, those few crates were effectively contained within the previous 2 crates. So you were compiling that code anyways, but it was just on 1 code gen unit in 1 crate. Now you have it split out, and now you have it working a lot more independently. Does that make sense? Does that answer? Great. See a couple other questions here.
Okay. Do over here, I guess.
What was the process of negotiating the common XML crate like? How did you guys work out disagreements when you were doing that?
It was very nice. We usually figured out, what can we share, and usually that starts with, okay, well, first off, identify what you already have in common, and identify what can be done without I/O. I do feel like sans I/O really helps here, right? Because it's usually very easy to tell when you're doing I/O because you have to deal with I/O. So you just figure out where that border ends and begins and extract that out. You aren't able to do it completely. There's some stuff that gets a little bit interfered between simply because networking is hard and GUI is substantially harder. But I think that's a good rule, right? Figure out where the I/O is, and that usually provides a good border for what can be shared.
All right. Thank you so much, John. I really appreciate the talk. If you could hear it for John. Thank you so much. Thank you so much. All right. Up next, we have Veronica. Some may know her as versecafe, and going to be talking about SDKs and the Rust ecosystem. Yeah, whenever you're ready.
To anyone who uses Zed, beautiful editor. Thank you, Michaela. It's wonderful. So I guess my main thing is I don't actually get the opportunity to write that much Rust anymore. My main project at work is half TypeScript, half Zig. But given that, I still want to make all of my tooling accessible to people in the Rust ecosystem. And while yes, you could always just fetch stuff with raw requests and suffer, write CERD everywhere, and it's doable. There is a better way for anyone who is civil enough to do open API generation, which if the thing you're working with doesn't have that, you just probably shouldn't use it. So kind of a rule of thumb. But anyways, almost every modern project either has open API SD generation right now or can easily add it. This, for example, is Alicia. It's a modern TypeScript framework, but it's good enough for a demo. So there's just super simple setup here, endpoint now, response schema, types, details. All of this, though, is mostly optional, to be fully honest. You could delete the type part, you could delete the detail part, and you could maybe delete the response part, although I wouldn't. And you will still get out something mostly useful. You will still get out a schema that just has a response that returns a string. Basics here are kind of twofold. One side is, as someone who's using Rust, working with external projects, is the actual SDK generation from what you have. And for that, I am actually using something fully open source, which is Progenitor. I do not know if anyone has used this before, but it is an extremely simple. Wonderful. It is super, super simple to get set up. You can literally just point it at a API JSON file, and it works. One line, nice importable library. Just grab it, spin up a client, and then get right off to the races. So in this case, I have actually made this very, very friendly for SDK generation because what we have done is the detail field, so operation IDs, as you'll see, correspond to the actual name of the parameters you get out in your SDKs. If you don't include this, or if you're working with a API that doesn't include it, that is all right. You will still get something useful. It will just probably look like this. So a little less legible, might not have docs on it, but you'll still get the right shape. You'll still get a usable API. But as you further refine this, say you work at a Python shop or a TypeScript shop and you want to write something in Rust, but your boss won't really approve of it for the main thing. You know how it is. You can always refine your things further. So you can go in and you can go description IDs for SDKs, but if you maintain the library, you know how it works. But more importantly, you can go in and you can start specifying. So instead of just hey, this is a string. You can do things like, hey, this is a date time. When you do this, OpenAPI specs will get out date as a specialized string field. So when you work with a library that supports it, like Progenitor in this case, not only do we get a string here, for now, we actually get, no, type now, but more importantly, when you get to it, it is a real date time. It is actually usable. You can take this, you can turn it into any kind of RFC string, anything else. You can plumb it through the rest of your Rust tooling. No decoders everywhere, no CERD, just works. And you can go off to the races with it. I actually don't have that much more to say. I do have a far, far fancier demo commented out below, but I need like a couple more minutes of setup on that. But yeah, up to if anyone has questions or if people actually want to see what this looks like on a large full-scale project, if I can get it running locally.
It's a very cool project. Can we see do you see the API for the large project?
Yes.
Maybe not run it, but I'd love to see the JSON just as a.
It is a very, 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 very large JSON.
Right.
This API has something like 300 endpoints right now. This
Wow.
powers an entire Git forge. And actually, I do have a little more to cover in this demo. It's just hard to see, which is working with slightly incompatible APIs. For example, you can technically do this in a build.rs, but I'm lazy and threw it in a Python file. The actual API you get back from my production server is not compatible with Progenitor because it is OpenAPI 3.1 instead of 3.0, which means it has nullable true as its way of defining null, whereas classical SDK version 3 is technically any of the actual type and then null, which is a really weird pattern. They regret that heavily because it doesn't actually work with like JSON schema emission, but that's still what most of the ecosystem tooling is on. So I have a processor here, which just kind of goes through, drops the cookie field because it's not supported, converts the any ofs nicely, just trims out null branches. And then another thing, my framework here, Alicia, outputs application JSON, multi-part form data, and octet streams for all of its acceptable data types inwards because it's hyper flexible. Annoyingly, most SDK generators don't support that. So I just have a simple script that goes in and just strips everything but JSON because JSON works everywhere and it's beautiful. And then just go in, there's some other little things around like deduping and little things that Progenitor doesn't support perfectly. But overall, this is about 130 lines of relatively quick Python scripting to filter out and parse the entire raw, not really meant for a Rust SDK outputs that just power my docs and turn it into a Rust SDK, which maybe there will be a demo of. Depends. But I can at least demo the types on this, which is this is very hard to do while looking sideways.
Yeah. While you're looking at this, does anyone have any questions? All right.
But so fancier demo here. Not going to share the actual API on this because I don't have it working locally right now because I'm rushing this. Is you can also do with Progenitor builder patterns, which make things much, much nicer when working with more complicated APIs, like a forge, for example, where every single endpoint you'd be specifying this org, this repo over and over and over again. Whereas instead in here, you can come in and I can go, I'm doing repo search. The org owner is myself, the name of the repo is Webbles, and I can take this and I can just clone it, and then I can write a query for, this runs to git grep basically, but give me every instance of RSS mentioned in the library, give me every instance of Atom feeds, right? And then as I go down, I just have a nice matches field, which Progenitor beautifully encodes as a vec. I can take it, I can iterate over it, and I can just print every single match here. And this saves me probably 100 lines compared to doing this raw with CERD, decoding and encoding everything. And all it took was a one-time cost of a little bit of a Python script to clean it all up. But that's everything.
Awesome. Thank you so much, Veronica. All right. Lovely, lovely for that amazing demo. Up next, we have George Huh with CocoIndex talking about building a Python library, a Rust core for search indexing. So yeah, welcome up.
Hello everyone. I'm George, co-founder and the CTO of CocoIndex. And CocoIndex, basically, we are an open source framework for incremental data processing. And basically, the idea is simple. Like, you have a bunch of source data, which can be different documents, can be code base, can be like whatever database, and put into your functions logic written in Python, and then after transform them, you put into some target, which can be different database, vector index, knowledge graph, whatever you pick. And the most important thing part is that CocoIndex is an incremental data pipeline, means it's the source are keep changing. The new data added, existing data keep updated as is deleted, and you don't need to worry about that. And we CocoIndex keep the target in sync with the source after transform, and we only do the incremental processing. So the unchanged part you don't waste the recomputing, but we do the minimum recomputing, and in a way it's similar to a motorized wheel. If many people from with data background may be familiar with, but it's more in a more generic sense. You can put any Python logic, like not only a simple SQL logic. And this one framework is built using a Rust core, and but it's called a Python SDK. Users write code in Python. So this is one part is a little bit unusual for CocoIndex, that we see a lot of other projects using like C++ or Rust. This basically more efficient language, compile time language for data plane or for compute part, and then they wrap as a Python SDK. For example, like PyTorch, NumPy, like they have Python SDK, and but in CocoIndex, like we are doing a kind of the opposite side. Like we user the compute part is written in Python, like because it's users code, and a lot of our users they are familiar with Python, but we use the Rust. We have a Rust core. The Rust core is more like a control plane. So, for example, you're doing something like bookkeeping, dependency tracking, change detection, scheduling, maintain some states, this type of thing. But this still benefits a lot from Rust. For example, they have a static, very strong type system to capture problems very early, so make our framework very robust. And also, like another great benefit is that we expose the core in Rust, but different other language like Python, like in the future, we may even expose API for TypeScript, JavaScript, and Go, and a lot of other language, and also for Rust itself. So we are more, we are not binded to a single language SDK. So now I'm going to talk more about some stories and some lessons we learned when building this. And so basically, we have a Python SDK, and which is user code here, and the Rust core we maintain states, do change detection, and do some user code scheduling. The Rust lab core figure out, okay, which part of user code needs to be executed, which can be skipped because of, for example, no data change, things like that. And also in Rust core, we leverage IOMDB. I will talk more details later. We leverage that to persist these states and keep track of the data, the change tracking part. This is the user code written in Python. So it's very simple. For example, they can write a function like this, add some decorator, and then this is basically a basic compute unit, and then they can use some API to consider similar to a React component, basically. You mount this function means similar to a React component, and so if the input they don't change, the next time when the main function is rerun, it will skip the compute. But if it's changed, it will run this, and it help you to keep track all the outputs. So which means you can, if the input file is gone, the output generated last time will also be cleared by the framework. This is a highlight idea. The code is very simple. This is what users write. And the underlying, we use the PyO3 to wrap a Rust engine and export that as a Python SDK. So and we use the PyO3 basically they expose a more maturing tool to help to build. I build time with this Rust core in PyO3 built as a dynamic shard library, and they packaged with the Python we released together. On Python side, basically, because different Python version, they have different minor API, but they're also a shared API called API3, which is compatible to multiple Python versions. So we only release one version per target OS and per architecture. Different Python versions share the same one. And on Rust side, one important thing is that our core engine have zero dependency on Python itself. We have two crates basically. One crate is the core crate. This crate has zero dependency. The other crate is the PyO3 wrapper, which bridges the Python SDK and the Rust. So the core engine, the core crate, we declare a trait like this. And the PyO3, the Python specific crate, implement this trait, provide an implementation for that trait. So this one provide a lot of flexibilities. So in the future, when we are going to support other language, for example, JavaScript, we just provide another implementation for this trait. Then we can, for example, expose another API through the NAPI for JavaScript. And then this type associated type today in the Python specific trait, there are PyO3 ones, and in case it will be the NAPI types. And there's one thing is a little bit a little bit heavier, but still work pretty well. Is that there's a two async runtime running at the same time. Rust using the Tokyo, which is a pretty standard, and Python, because users still write the async code, is need to running in the Python async IO. There are two event loop, and but this works well. Like I think it depends on the case. Sometimes like there can be tasks, async tasks created on Python side. Then Python own that, and Rust they can still await that through a bridge provided by the PyO3. And on the other side, the same. Sometimes Rust side for some functionality we need to have some Rust owned async tasks owned by Tokyo, and Python side they can through another bridge we can wait for that. Just make the ownership clear, and two event loop they can coexist, cooperate pretty well. And another pretty important part is the GIL, because in Python, although after 14 there's free-threaded Python, but currently most users are still using the before the 3.13, which is use the GIL. So we still need to deal with the GIL, and so they need to be pretty disciplined. For example, we want to avoid heavy computations when holding the GLL, so that makes the there's still heavy operation on Rust side. It can be paralleled, and especially for blocking operations, you definitely don't want to hold the GIL, and also you don't want to grab other logs with the GIL.
3-minute warning, just so you know. 3 more minutes.
Okay. And one important part is that the error propagation. So when user they write the Python code, the Python side, the error trace, they propagate through Rust layers, and then at the high level there can be a Python code from user. So it's from low levels Python, middle layer is the Rust. So through that we want to keep the structured error traces from the Python side. So means we cannot we want to use our own error type to make that to make sure keep all this structured information along the way. And LMDB, we totally use LMDB is support a very fast random reads, very efficient. But there's downside. The downside is the write. They only the write transactions must be exclusive. So we get the benefits of the efficient write read, but for write we solve the problem by batching the write transactions within Rust. This is our design basically. The interesting part is that for this batching, we end up with a very generic batching util, which not only benefits the LMDB, also benefits from other case. The case A is LMDB writes. Case B is like, okay, for users Python function. For example, for some user function, like call a model, which is you do that in batch for 100 input together. It's way more efficient than doing that one by one. So both of them are shared the same batcher util in Rust. For users, for this case, user just write a simple annotation on Python side, and they enjoy that benefit. And the last part is one thing that works. There's work not that well. There's some friction that when we do that, it means okay. Because we are releasing Python packages, so the Rust code need to be pre-built. So you cannot have these optional features. The feature size needs to be decided at build time. So means for these optional dependencies, pretty much we need to bring them up in Python side. For example, for this different database support backend, we bridge them in on as a Python SDK. So we keep this Rust core very still very slim. I think that is pretty much the most things we want to share today. Thank you.
Thank you so much for that talk. Yeah, appreciate it. CocoIndex sounds like a very fun project. Yeah, all right. Thank you so much. Up next, we have Inanna here to talk to us about Haskell and Rust, or writing Haskell in Rust, if I remember.
Embedding, yeah. So
Embedding Haskell
very
in Rust.
kindly, they let me do a silly one to. So this is a talk about that was inspired by something Maravas did in 2020, which was embedding Python in Rust, because why not? It sounded like a fun idea at the time. In similar spirits, I'm going to ask you to suspend disbelief until you get to the end. This is silly. I wanted to see if it would work. It does have some applications. Cool. With that in mind, so the fundamental shape of this, GHC, Glasgow Haskell compiler, compiles the language known as Haskell, which is a strongly typed high-level functional programming language. It's great for fun projects. Don't use it to interact at the systems level. It is. I write Rust for a living. I don't write Haskell for a living. There's a reason for that. But it emits a intermediate representation called core, which is then embedded in a Rust binary and compiled by a Cranelift to native runtime. And then you have no GHC in the runtime. So we're going to start immediately with actually running something. So first, let's see what the Haskell stuff is. So you have a effect, two effects, right? Console, where you can emit a string, and await integer, where you just await an integer typed by the user, and RNG, where you get a random integer. That's it. That's the thing. That's for this quick demo. So then you have in Rust, you have a couple effect handlers that actually handle the execution side of this. So if you're running, if you're emitting a line, it's just print line. If you're awaiting an integer, it's a little bit more complex. It's doing all of the interacting with the real world stuff that Haskell really doesn't want to do. And the same thing for the random number generator, right? So then this is all in service of being able to write Haskell inline, where you have a game, and this isn't an effect stack, so this actually doesn't have I/O at a structural level, right? So you have a pure sandbox, no I/O, only effects in this effect monad, which you can see here has just console and random number generator. So target, you're looking for a random number, and then you loop, and then you just repeatedly await integer until you get the correct guess, too low, too high. I mean, you're at a Rust meetup. This isn't a language you're familiar with. This is very simple. So what that actually looks like in practice, this is the one section where I'll actually run at something, and hopefully, yep, cursive demos is not biting me yet, but you do get to watch me try to guess a number on screen. And wait, I did 40 already. Right, well, that is super anticlimactic, but it also works for a bunch of other stuff. This is just, it did something, I was willing to type it out on a screen in front of the talk. Now, let's talk about the crazy stuff. All right, so what happens, and this is the fundamental question that I made this to answer, what happens when you give LLMs interaction with Haskell as their primary computer use interface, right? Because they're just these little guys that run their computers, we want to mess with them, we want to make them write Haskell for fun. It's, why not? So quick recap. So Tidepool is an MCP server, Model Context Protocol. It's the standard tool used for LLMs. Think of it as USB-C. It's how you take an arbitrary thing and plug it into an LLM. And here we're thinking like Claude Code, Codex, Gemini CLI, whatever. It's how you add tools to them, right? So it exposes two tools, one of which is eval, which runs Haskell in the sandbox. Again, no I/O, only a pre-approved set of effects. and resume, which I'll explain soon, which continues a paused computation. And Haskell is great for weird stuff like that. So as is traditional, we start simple, right? So you just have 1 plus 2. Wow, it works. This is great. Your LLM can write 1 plus 2, and it's evaluated in Haskell. So you also have more complex stuff, and this is where it gets interesting, right? So let's say you're reading a file, you're counting the number of lines there, and then you're outputting something via say. And you can see that it does say cargo.toml is 29 lines, and then the pure line count returned at the end is the results. Hopefully this all makes sense. If like I'm just like talking to, or anyway, please raise your hand if any glaring questions come up. So the effects do compose, and you can run programs, you can output stuff as before, you have access to a KV store, you have access to some of the full Haskell, like Haskell is very good at composing effects and like manipulating strings and stuff. It's not good at systems work. That's why I'm at a Rust meetup. I actually started trying to have LLMs write Haskell out of curiosity to see what would happen. They do amazingly at type level DSLs, complex monadic stuff, applicative, whatever. But then you ask them to write a database interaction and they just they stub it out because there's nothing in the distribution. There's no training data for Haskell interacting with the real world. That's fine. We use it for composing the effects and we use Rust to interpret the effects. That's kind of the point of this. So here's why this is interesting for LLMs and a way that's not just about dunking on Haskell, which I have been paid to write Haskell. I can dunk on Haskell very well. Find me later. Right. So if you've used Claude Code or any other coding agent, breathing for a second, you've probably seen something like this. God-awful bash script that uses bash as a composition primitive using various like sed, awk, sort, etc. to accomplish a task in a single call. Now, this is actually worth having despite its lack of inherent beauty, precisely because inference is expensive. Every time you hit an LLM backend to do inference, which is predicting the next set of tokens, you pay someone money, right? This isn't a free operation. So if you can pull everything for like 4 separate tool calls into one ungodly mess of bash, then it's worth the ungodly mess of bash precisely because you're not paying like Anthropic or OpenAI or like, God forbid, probably not Grok. I hope you have taste. Anyway, you're like not paying some like third-party money for each call, and it's worth the like additional local ugliness, right? So this is a similar pitch, except instead of like ugliness, it is galaxy brain. So the idea here is this does the exact same thing. SG find is just AST grep, like just via the library access. You've got some like nice like, you're using the like honestly very good like string manipulation and sequence manipulation, etc. Using monadic sequencing, and you're using it to get the same thing. Now, the benefit of this is aside from beauty, like, okay, so the reason this is a Rust meetup, among other things, is LLMs write better code when there are constraints, when there are compile errors, when things have a like well-known type level shape, and when they're not like this, right? If an LLM wrote code, or if one of your colleagues wrote code with an LLM that looked like this, you would probably not commit this, right? Like, I don't trust an LLM to do something entirely right with this kind of bash. I trust it to like 75% right. And whereas with this, if it gets something lined up wrong, it'll be a compile error, which is better. Right. So that's the core thesis. Something cool that you get for free from this, I mentioned resuming a paused computation earlier. So this is just pure code, no effects, but like something that's deliberately tuned to produce a very large output JSON. You can see it's replicating lorem ipsum 1 to 200. Right. So if you call Tidepool eval up here, the MCP, full MCP, with this, what you actually get is everything that's over the size budget is automatically stubbed out in a tree-aware way. So this is just free, right? You just get this on every Tidepool output. And here you can see there's just a large list and a string. Both of these are identified as stubs with the size. and it's marked as suspended. There's a continuation ID. And then in the next call, you can have the LLM itself can be like, oh, I want more of that. Let me see the rest of the values. And then it's like, all right, there's still 1 to 47. This is over my budget. Here's more in a stub I can expand. And then maybe you go to expand the other stub in the first continuation. And again, you get a bunch of lorem ipsums and etc. So the idea is that often LLMs will just read the entire world, and instead of letting them do that, you can just have them in a tree structure aware way read everything and then just get like oh, would you like to click this to see more? Which is, it's handy, right? It's a neat trick, but it's not enough motivation for that. What I'd really like you to focus on is that we get this for free, basically. Just having hunt continuations, I was like, oh yeah, that would be cool, and then I implemented it. It was really easy. So you can do more stuff with that, right? You can have, say, files. You're grabbing a blob-based search for the Tidepool repo, whatever. This is written by an LLM, but like this is also a tool interface I made for LLMs to use. So I hope you forgive me for that part. These are, actual tool calls written by LLMs using the tool. And then you have ask, where it automatically pauses the computation. And here it's like, I don't know, like a list of files, and then the LLM itself can, at that pause point, provide a number that's then like, which of the file lists do you want to read, right? So you end up being able to build, instead of just bash scripts that like run, you end up being able to build complex logic that pauses at critical decision points for the LLM to steer, which is, it's like a neat trick, right? And this is like a neat like test bed to do stuff like that very quickly, which is a lot of the benefit of Haskell. You can do galaxy brain stuff very quickly, right? Like you could write your weird compiler hobby project in Rust, just, you could do that, but it's easier in Haskell. And then you make it production ready and you rewrite it in Rust. It's great. It's the way of the world. So complex effect sequences. Here you have something kind of similar to the previous one. It's using the AST grep again. It's grabbing everything that matches this name and fields pattern. And then it's outputting via the basically print line with say. And then here, and this is the interesting part, it actually has LLM as an effect. So this just like, it could hit like a local LLM if you have a computer that can support local LLMs. This is a MacBook Air, it cannot. Or in this case, it's hitting Haiku, which is the just absolute cheapest Anthropic LLM that they have available. So you're basically able to embed little heuristics in your complex logic. So you end up with this complex chain of logic running like recursive, effect composition, everything, whatever. And it can pause to ask the LLM that spawned it for guidance, or it can shell out to a much dumber LLM for like a back of the envelope sort of like squint. Does this look like a data config or handler? Which, sure, why not? And then it can do like key value stuff, etc. And it can also, yep, I'll get that when I'm done. And then it can also use the full power of Haskell's JSON interface, which is pretty neat. It doesn't fully utilize it here, but there's a library called ASON Lens, which is quite nice, that allows for lenses, if you're familiar with them, as basically a way of composing a selector over JSON. So you can use essentially the best parts of Haskell, which are composing pure logic, working with complex recursive structures and lenses, and like type level DSLs. And you don't have to work with the worst part of Haskell, which is engaging with the real world. You have the Rust entirely does that. Like every one of these effects shells out to Rust code that interprets it and returns it to Haskell. And because it's effect based, because it's in an effect stack, there's no IO. Like at a structural level, when like Cranelift is run to turn the intermediate representation core into something that can run inside Rust, there's no escape hatch. There's no unsafe perform IO. There is no ability to reach out and mess with the real world. So like if you want to run LLMs that you don't entirely trust, which is a good practice, you shouldn't, you can like give them this like hyper restricted but equally hyper expressive interface where they can only do the effects you say they can, like full stop, but they can do all kinds of things composing those effects. things. And right, that is the last slide. So, like I said, thanks for letting me do a silly one. Questions?
Very quick question. Do you think that Haskell, as this intermediate layer between LLMs and Rust, do you think it has other potential uses, being familiar with the layer, for example, as an intermediate representation for compilers?
So, sorry, did you say an intermediate representation of the BIOS?
For compilers, sorry.
Oh, for compilers, yes. I'm not really sure. I think if you're building a compiler, I actually also have a toy language that I built with this, where it does all the parsing with test and then like shoves that over into Haskell to do the evaluation. I think you might have a good time with that if that sounds like fun to you. But let's talk more about that later. And someone else had a.
Hello. So my question is, you spent a lot of time in this talk talking about how you can use this for LLMs. What I'm curious about is, can you use this to use Haskell, the scripting layer, for a Rust project?
You could do that, yeah. If you want to have a Rust project where your like user interface is just writing Haskell, but you don't trust your users not to write unsafe perform IO, delete my server, you could also give this to humans. You just have to find humans who like Haskell.
Can I use this to intern proof my code base?
To intern proof your code base.
Yeah. I'll write the IO. They don't have to worry about it, and I just stick them in the corner with Haskell, and I can recruit all of, the college functional programmer people who can't actually get jobs.
I honestly, maybe. There's a reason I work in Rust instead of Haskell. I will say, if you learn Haskell, you will have some fun. It's a bunch of interesting puzzles. You might not get a job working with it.
Okay, I think we only have time for one more question, if there is one back here.
Hi, so this is kind of a half joke and half serious question. The joke half is, when can we swindle the next VC to pay for all of this so that we could build a new durable function stack? That's the joke part. Here's the real part. How do you see this sort of improvement over, say, TypeScript as a more common lingua franca for LLMs to author, like compared to this? Because you mentioned like, okay, a lot of them have training data, but I feel like still a big difference between an LLM's capability of writing TypeScript versus its capability of writing whatever dialect of Haskell has been enabled.
Pretty fair. I will just say that there's way more Haskell training data than you think would be out there based on job staff, because if people like Haskell, they really like talking about Haskell. There is a lot of, like, LLMs can write a good type level DSL, they can write good Haskell. Like, it's more in the training data than you would expect. But honestly, I wrote this because I was test driving a new agent orchestration harness I was making, and I wanted something that was kind of insanely ambitious and that wasn't literally just re-implementing C or a browser. No, you re-implement Git.
Thank you so much
for
for the lovely talk. That was very, very inspiring. All right, well, thank you so much, everybody, for coming along, and thank you for bearing with us as we're learning how to do these as well. This is actually my first time emceeing, so this has been fun. And I, in particular, want to thank Convex for hosting us, and Wayne over here. If everyone could give Wayne a good hand. He made sure all this was possible, got the AV, he's been helping us with this. He's fantastic. And yeah, that's kind of it. There's QR codes with our Discord, and I'm going to put it up on here as well. If you want to join, we can talk. You can submit talks if you're interested in doing one here. Just come in there and post about it. We have a channel for that and everything. And thank you all for attending, and I hope you all have a fantastic Wednesday. All right.